Hi, my name is Natalie Ibarra, and today I'm going to be talking about my protein C, MCR1 for the Protein Project Part 2 aspect. So, starting off, I'm going to introduce the protein. So, MCR1 is a G protein coupled receptor. It's found in the melanocytes where it's the pigment producing cell in the skin and the hair follicles. It's set in the cell membrane where MCR1 functions as a key regulator to manage pigmentation by determining the amounts of eumelanin and pheomelanin. And some of the genetic changes of MCR1 can cause a lot of differences in pigmentation in humans, which can sometimes result in red hair or fairer skin. So looking at my, overall 3D shape of my protein, so it exists as a helical protein structure inside cell membranes, which belong to the GPCR family. The receptor has 7 membranes spanning alpha helices and functions through the joining of the intra and extracellular loops between them. The extracellular section accepts the melanosortin signals before passing information through gene proteins that exist within the intracellular area. So for my project, what material I might use to mimic the shape in our model, I really didn't want to go out to the store and buy something, so I tried to figure out something that I had. So I had a lot of paper, I had yarn from, just clubs and all that stuff. So I decided to use, make paper balls to represent, amino acids, and then I used the yarn to, represent the polypeptide chain of the protein, and then just using, I wanted a background because I couldn't really make it, yarn stand up on its own, so I needed to lay it on something, and then I realized I could use the background for the cell membrane, and then when I was doing the project, I realized that I didn't have any of the alpha helices or any of the beta sheets. So then I searched that up and I was like, oh, how can I use this? How can I represent this? And I remembered that back in elementary school or middle school, to make those little coils, we would shed paper between the scissors. And I was like, okay, I could do that for the alpha helices, but for the beta sheets, I just folded slices of paper in different directions. I don't think that my protein contains any subunits, just because I just wanted to focus on showing one chain, and I didn't really want to show many more than that. But if I had to, I guess I would represent it with a different color of yarn and just join them there, So for question 3, I feel like I was able to represent this pretty well. I do have the linear sequence of amino acids. I feel like you can see that well. I did include the alpha helices and the beta sheets, and I do think that I did show a full 3D shape of a single polypeptide chain. But as for the 4th degree, again, I would only be able to show that if I created multiple chains interacting and I only constructed one. So for question 4, the assigned mutation, it can form disulfide bonds, which can have many different outcomes. It just basically disrupts local interactions. I decided to just build one model and then switch it out with another piece of something that I had in my room. And then I just took 2 pictures, one showing the arginine and then the other one the cysteine, to highlight the structural change at position 67. So for question 5, it can affect the protein's function. It can change the protein's 3D structure, harming its ability to bind ligands or activate signaling pathways, and just affecting its overall stability. It can lead to cellular dysfunction, such as altered melanin production in melanocytes, impacting skin and hair pigmentation, which also can increase the risk to UV damage and melanoma. For question 6, to represent this well in the model, I just used labels. It was the most simplest way to showcase it. And then 3 limitations, probably like the lack of atomic detail. There's no actual atomic interactions. I really simplified the folding representation, so it's like less dynamic and complex. And it's also just missing like environmental factors. It just fails to account for cellular interactions.